Modern digital and analog communication systems. BP Lathy Xi Ding. Modern digital and analog communication systems. International 4th edition. B. P. Lathy, Professor Emeritus, California State University Sacramento. Xi Ding, Professor, University of California Davis, New York Oxford, Oxford University Press. 2010 Oxford University Press, Inc. publishes works that further Oxford University's objective of excellence in research, scholarship, and education. Oxford, New York. Auckland, Cape Town, Dar es Salaam, Hong Kong, Karachi. Kuala Lumpur, Madrid, Melbourne, Mexico City, Nairobi. New Delhi, Shanghai, Taipei, Toronto. With offices in Argentina, Austria, Brazil, Chile, Czech Republic, France, Greece, Guatemala, Hungary, Italy, Japan, Poland, Portugal, Singapore, South Korea, Switzerland, Thailand, Turkey, Ukraine, Vietnam. Copyright 1983 by CBS College Publishing, copyright 1989 by B. P. Lathy and Saunders College Publishing, a division of Holt, Reinhardt, and Winston, Inc., copyright 1995, 1998, 2010 by B. P. Lathy. Published by Oxford University Press, Inc. 198 Madison Avenue, New York, New York, 10016. http://www.oup.com. Oxford is a registered trademark of Oxford University Press. All rights reserved. No part of this publication may be reproduced, stored in a retrieval system, or transmitted, in any form or by any means. Electronic, mechanical, photocopying, recording, or otherwise. Without the prior permission of Oxford University Press. Library of Congress cataloging in publication data. Lathy, B. P. Bhagwandars Pannalal. Modern Digital and Analog Communication Systems, B. P. Lathy, Xi Ding, 4th ed. P. C. M. ISBN 978-0-19-538493-2, hardcover, ALK. Paper 1. Telecommunication systems. 2. Digital communications. 3. Statistical communication theory. I. Ding, Xi, 1962, 2. Title 5101 Tarkis, L. 333 2008. 621.382 DC 22-2008029440. Printing number 987654321. Printed in the United States of America. On acid-free paper. Brief table of contents. Preface xvii. 1. Introduction. 2. Signals and signal space. 20. 3. Analysis and transmission of signals 62. 4. Amplitude modulations and demodulations 140. 5. Angle modulation and demodulation 202. 6. Sampling and analog to digital conversion 251. 7. Principles of digital data transmission 326. 8. Fundamentals of probability theory 393. 9. Random processes and spectral analysis 456. 10. Performance analysis of digital communication systems 506. 11. Spread spectrum communications 614. 12. Digital communications under linearly distortive channels 666. 13. Introduction to Information Theory 734. 14. Error correcting codes 802. Or orthogonality of some signal sets 873. B. Cauchy-Schwarz Inequality 875. C. Gram-Schmidt Orthogonalization of a vector set 877. D. Basic matrix properties and operations 880. E. Miscellaneous 885. Index 889. VCONTENTS 1. Preface xvii. Introduction. 1.1 Communication systems. 1.2 Analog and digital messages 4. 1.2.1 Noise immunity of digital signals 4. 1.2.2 Viability of distortionless regenerative repeaters 5. 1.2.3 Analog to digital DJ conversion 6. 1.2.4 Pulse-coded modulation digital representation 7. 1.3 Channel effect, signal-to-noise ratio, and capacity 9. 1.3.1 Signal bandwidth and power 9. 1.3.2 Channel capacity and data rate 10. 1.4 Modulation and detection 11. 1.4.1 Ease of radiation, transmission 11. 1.4.2 Simultaneous transmission of multiple signals multiplexing 12. 1.4.3 Demodulation 13. 1.5 Digital source coding and error correction coding 13. 1.6 A brief historical review of modern telecommunications 15. VV contents 2. 3. Signals and signal space 20. 2.1 Size of a signal 20. 2.2 Classification of signals 22. 2.2.1 Continuous time and discrete time signals 23. 2.2.2 Analog and digital signals 23. 2.2.3 Periodic and aperiodic signals 24. 2.2.4 Energy and power signals 25. 2.2.5 Deterministic and random signals 25. 2.3 Unit impulse signal 26. 2.4 Signals versus vectors 28. 2.4.1 Component of a vector along another vector 28. 2.4.2 Decomposition of a signal and signal components 30. 2.4.3 Complex signal space and orthogonality 32. 2.4.4 Energy of the sum of orthogonal signals 34. 2.5 Correlation of signals 34. 2.5.1 Correlation functions 35. 2.5.2 Autocorrelation function 36. 2.6 Orthogonal signal set 36. 2.6.1 Orthogonal vector space 36. 2.6.2 Orthogonal signal space 38. 2.6.3 Parsevals theorem 39. 2.7 The exponential Fourier series 39. 2.8 MATLAB exercises 46. Analysis and transmission of signals 62. 3.1 A periodic signal representation by Fourier integral 62. 3.2 Transforms of some useful functions 69. 3.3 Some properties of the Fourier transform 75. 3.3.1 Time frequency duality 76. 3.3.2 Duality property 77. 3.3.3 Time scaling property 79. 3.3.4 Time shifting property 81. 3.3.5 Frequency shifting property 83. 3.3.6 Convolution theorem 87. 3.3.7 Time differentiation and time integration 88. 3.4 Signal transmission through a linear system 90. 3.4.1 Signal distortion during transmission 92. 3.4.2 Distortionless transmission 92. 3.5 Ideal versus practical filters 954. 5. 3.6 Signal distortion over a communication channel 97. 3.6.1 Linear distortion 97. 3.6.2 Distortion caused by channel nonlinearities 99. 3.6.3 Distortion caused by multipath effects 101. 3.6.4 Fading channels 103. 3.7 Signal energy and energy spectral density 103. 3.7.1 Parsevals theorem 103. 3.7.2 Energy spectral density ESD 104. 3.7.3 Essential bandwidth of a signal 105. 3.7.4 Energy of modulated signals 108. 3.7.5 Time autocorrelation function and the energy spectral density 109. 3.8 Signal power and power spectral density 111. 3.8.1 Power spectral density PSD 111. Contents 1x. 3.8.2 Time autocorrelation function of power signals 113. 3.8.3 Input and output power spectral densities 117. 3.8.4 PSD of modulated signals 118. 3.9 Numerical computation of Fourier transform. The DFT 118. 3.10 MATLAB exercises 123. Amplitude modulations. And DEMODULATIONS 140. 4.1 Baseband versus carrier communications 140. 4.2 SSIDEBAND amplitude modulation 142. 4.3 amplitude modulation AM 151. 4.4 bandwidth efficient amplitude modulations 158. 4.5 amplitude modulations, vestigial SIDEBAND, VSB 167. 4.6 local carrier synchronization 170. 4.7 frequency division multiplexing FDM 172. 4.8 phase locked loop and some applications 173. 4.9 MATLAB exercises 181. Angle modulation and demodulation. 5.1 Nonlinear modulation 202. 202. 5.2 Bandwidth of angle modulated waves 209x contents. 6. 5.3. 5.4. 5.5. 5.6. 5.7. 5.8. Generating FM waves 222. Demodulation of FM signals 231. Effects of nonlinear distortion and interference 234. Superheterodyne analog AM/FM receivers. FM broadcasting system 241. MATLAB exercises 242. 239. Sampling and analog to digital. Conversion 251. 6.1 Sampling theorem 251. 6.1.1 Signal reconstruction from uniform samples 253. 6.1.2 Practical issues in signal sampling and reconstruction 258. 6.1.3 Maximum information rate, 2 pieces of information per second per Hertz 262. 6.1.4 Non-ideal practical sampling analysis 263. 6.1.5 Some applications of the sampling theorem 267. 6.2 Pulse code modulation PCM 268. 6.2.1 Advantages of digital communication 270. 6.2.2 Quantizing 271. 6.2.3 Principle of progressive taxation, non-uniform. Quantization 274. 6.2.4 Transmission bandwidth and the output SNR 278. 6.3 Digital telephony, PCM in TL carrier systems 281. 6.4 Digital multiplexing 285. 6.4.1 Signal format 285. 6.4.2 Asynchronous channels and bit stuffing 287. 6.4.3 Plesiochronous almost synchronous digital hierarchy 288. 6.5 Differential pulse code modulation DPCM 290. 6.6 Adaptive differential PCM ADPCM 294. 6.7 Delta modulation 295. 6.8 Vocoder dollar and video compression 300. 6.8.1 Linear prediction coding vocoders 301. 6.9 MATLAB exercises 3107 Principles transmission of digital 326 data. 7.1 Digital communication systems 326. 7.1 L source 326. 7.1.2 line coder 327. 7.1.3 multiplexer 328. 7.1.4 regenerative repeater 328. 7.2 line coding 329. 7.2 LPSD of various line codes 330. 7.2.2 polar signaling 334. 7.2.3 constructing a DC null in PSD by pulse shaping 336. 7.2.4 on-off signaling 337. 7.2.5 bipolar signaling 339. 7.3 pulse shaping 343. 7.3 LLN tersymbol interferences ISI and effect 343. 7.3.2 Nyquist's first criterion for zero ISI 344. 7.3.3 Controlled ISI or partial response signaling 350. 7.3.4 Example of a duobinary pulse 351. 7.3.5 Pulse relationship between zero ISI, duobinary, and modified duobinary 352. 7.3.6 Detection of duobinary signaling and differential encoding 353. 7.3.7 Pulse generation 355. 7.4 Scrambling 355. 7.5 Digital receivers and regenerative repeaters 358. 7.5 L equalizes 359. 7.5.2 Timing extraction 363. 7.5.3 Detection error 365. 7.6 I diagrams, an important tool 366. 7.7 PAM, Mary baseband signaling for hire. Data rate 369. 7.8 Digital carrier systems 372. 7.8 L basic binary carrier modulations 372. 7.8.2 PSD of digital carrier modulation 374. 7.8.3 Connections between analog and digital carrier. Modulations 376. 7.8.4 Demodulation 377. 7.9 Mary Digital Carrier Modulation 380. 7.10 MATLAB Exercises 386. Contents Shishi Contents 8. 9. 10. Fundamentals of Probability. Theory 393. 8.1 Concept of Probability 393. 8.2 Random Variables 408. 8.3 Statistical Averages Means 427. 8.4 Correlation 436. 8.5 Linear Mean Square Estimation 440. 8.6 Sum of Random Variables 443. 8.7 Central Limit Theorem 446. Random Processes and Spectral Analysis 456. 9.1 From Random Variable to Random Process 456. 9.2 Classification of Random Processes 461. 9.3 Power Spectral Density 465. 9.4 Multiple Random Processes 479. 9.5 Transmission of Random Processes through Linear Systems 480. 9.6 Application Optimum Filtering Wiener HOPF Filter 483. 9.7 Application Performance Analysis of Baseband Analog Systems 486. 9.8 Application Optimum PREMPHASIS Emphasis Systems 488. 9.9 Bandpass Random Processes 491. Performance Analysis of Digital Communication Systems 506. 10.1 Optimum Linear Detector for Binary Polar Signaling 506. 10.1.1 Binary Threshold Detection 507. 10.1.2 Optimum Receiver Filter Matched Filter 508. 10.2 General Binary Signaling 512. 10.2.1 Optimum Linear Receiver Analysis 512. 10.2.2 Performance Analysis of General Binary Systems 5161 1. 10.3 Coherent Receivers for Digital Carrier Modulations 520. Contents xvii. 10.4 Signal Space Analysis of Optimum Detection 525. 10.4.1 Geometrical Signal Space 525. 10.4.2 Signal Space and Basis Signals 527. 10.5 Vector Decomposition of White Noise Random Processors 530. 10.5.1 Determining Basis Functions for a Random Process 530. 10.5.2 Geometrical representation of white noise processes. 531. 10.5.3 White Gaussian noise. 533. 10.5.4 Properties of Gaussian random process. 534. 10.6 Optimum receiver for white Gaussian noise. Channels. 536. 10.6.1 Geometric representations. 536. 10.6.2 Dimensionality of the detection signal space. 538. 10.6.3 Simplified signal space and decision procedure. 541. 10.6.4 Decision regions and error probability. 545. 10.6.5 Multi-amplitude signaling (PAM). 551. 10.6.6 MREQAM analysis. 554. 10.7 General expression for error probability of optimum receivers. 561. 10.8 Equivalent signal sets. 569. 10.8.1 Minimum energy signal set. 572. 10.8.2 Simplex signal set. 575. 10.9 Non-white colored channel noise. 577. 10.10 Other useful performance criteria. 578. 10.11 NONCOHERENT detection. 581. 10.12 MATLAB exercises. 589. Spread spectrum. Communications. 614. 11.1 Frequency hopping spread. Spectrum FHSS systems. 614. 11.2 Multiple FHSS user systems and performance. 11.3. 11.4. 11.5. 11.6. Applications of FHSS. 621. Direct sequence spread spectrum. Resilient features of DSS. 628. 624. Code division multiple access CDMA of DSS. 618. 630 XIV contents. 12. 13. 1.7 Multi-user detection MUD. 637. 1.8 Modern practical DSS CDMA systems. 643. 1.8.1 CDMA in cellular phone networks. 643. 1.8.2 CDMA in the Global Positioning System (GPS). 647. 1.8.3 IEEE 802.11b Standard for Wireless LAN. 649. 1.9 MATLAB exercises. 651. Digital communications under linearly distortive channels. 666. 2.1 Linear distortions of wireless multipath channels. 666. 2.2 Receiver channel equalization. 670. 12.2.1 Anti-aliasing filter versus matched filter 670. 12.2.2 Maximum Likelihood Sequence Estimation MLSE 673. 12.3 Linear T-spaced equalization to C 676. 12.3.10 Forcing to C 677. 12.3.2 to C Design based on MMSE 679. 12.4 Linear Fractionally Spaced Equalizers FSE 684. 12.4.1 The Single Input Multiple Output SIMO Model 684. 12.4.2 FSE Designs 686. 12.5 Channel Estimation 688. 12.6 Decision Feedback Equalizer 689. 12.7 OFDM MULTICARRIER Communications 692. 12.7.1 Principles of OFDM 692. 12.7.2 OFDM Channel Noise 698. 12.7.30 Padded OFDM 700. 12.7.4 Cyclic Prefix Redundancy in OFDM 701. 12.7.5 OFDM Equalization 701. 12.8 Discrete MULTITONE DMT Modulations 702. 12.9 Real-life applications of OFDM and DMT 707. 12.10 Blind Equalization and Identification 711. 12.11 Time Varying Channel Distortions due to Mobility 712. 12.12 MATLAB Exercises 715. Introduction to Information Theory 734. 13.1 Measure of Information 734. 13.2 Source Encoding 7391 4. Contents xvii. 13.3 Error-free communication over a noisy channel 745. 13.4 Channel capacity of a discrete memoryless channel 748. 13.5 Channel capacity of a continuous memoryless channel 756. 13.6 Practical communication systems in light of Shannon's equation 773. 13.7 Frequency selective channel capacity 776. 13.8 Multiple input multiple output communication systems 781. 13.8.1 Capacity of MIMO channels 781. 13.8.2 Transmitter without channel knowledge 783. 13.8.3 Transmitter with channel knowledge 785. 13.9 MATLAB Exercises 789. Error correcting codes 14.1 Overview 802. 802. 14.2 Redundancy for error correction 803. 14.3 Linear block codes 806. 14.4 Cyclic codes 813. 14.5 The effects of error correction 822. 14.6 Convolutional codes 827. 14.6.1 Convolutional encoder 827. 14.6.2 Decoding convolutional codes 831. 14.7 Trellis diagram of block codes 837. 14.8 Code combining and interleaving 839. 14.9 Soft decoding 841. 14.10 Soft output Viterbi algorithm SOVA 844. 14.11 Turbo codes 846. 14.12 Low density parity check LDPC codes 854. 14.13 MATLAB exercises 861. Orthogonality of some signal sets 873. A. L. Orthogonality of the trigonometric and exponential signal set 873 xvii contents. A.2 Orthogonality of the exponential signal set 874. Cauchy-Schwarz Inequality 875. C. Gram-Schmidt Orthogonalization of A. Vector set 811. D. Basic matrix properties and operations 880. D. L notation 880. D.2 matrix product and properties 881. D.3 identity and diagonal matrices 882. D.4 determinant of square matrices 882. D.5 trace 883. D.6 EIGENDECOMPOSITION 883. D.7 Special Hermitian square matrices 884. E. Miscellaneous 885. E. LL1 Hopital's rule 885. E.2 Taylor and Maclaurin series 885. E.3 Power series 885. E.4 Sums 886. E.5 Complex numbers 886. E.6 Trigonometric identities 886. E.7 Indefinite integrals 887. Index 889 PREFACE International Edition. To Mount 30 Chief edition of Objective Technological was published. Of the Progress 4th at the International INSAME Communication Time edition. New systems software is to respond over and the teaching to decade the tremendous tools since have the also become available, making it much easier to provide solid and illustrative examples as well as more experimental opportunities for students. In this new edition, major changes are implemented to incorporate recent technological advances of telecommunications. To captivate students' attention and make it easier for students to relate the course materials to their daily experience with communication tools, we will provide relevant information on the operation and features of cellular systems, wireless local area networks (LANs), and wireline digital subscriber loop or DSL internet services, among others. Major revision. A number of critical changes are motivated by the need to emphasize the fundamentals of digital communication systems that have permeated our daily lives. Specifically, in light of the widespread applications of new technologies such as spread spectrum and orthogonal frequency division multiplexing (OFDM), we present a new chapter, Chapter 11, on spread spectrum communications and a new chapter, Chapter 12, on frequency selective channels and OFDM systems. As practical examples of such systems, we provide a basic introduction of current wireless communication standards including cellular systems and IEEE 802.1 LA/B per gram N wireless LAN systems. In addition, we summarize the latest DSL modem technologies and services. At the fundamental level, information theory and coding have also been transformed by progress in several important areas. In this edition, we include the basic principles of multiple input multiple output (MIMO) technology, which has begun to see broad commercial application. We also cover several notable breakthroughs in error correction coding, including soft decoding, turbo codes, and low-density parity check (LDPC) codes. To enhance the learning experience and to give students opportunities for computer-based experimental practice, relevant MATLAB examples and exercises have been provided in chapters that can be enhanced by these hands-on experiments. Organization. The fourth International edition begins with a traditional review of signal and system fundamentals and proceeds to the core communication topics of analog modulation and digital pulse-coded modulation. We then present the fundamental tools of probability theory and random processes to be used in the design and analysis of digital communications in the rest of this text. After coverage of the fundamentals of digital communication systems, the last two xvii-xvm Preface International Edition chapters provide an overview of information theory and the fundamentals of forward error correction codes. Ideally, the subjects covered in this text should be taught in two courses, one on the basic operations of communication systems, and one on the analysis of modem communication systems under noise and other distortions. The former relies heavily on deterministic analytical tools such as Fourier series, Fourier transforms and the sampling theorem, while the latter relies on tools from probability and random processes to tackle the unpredictability of message signals and noises. Today, however, with so many competing courses, it may be difficult to squeeze into a typical electrical engineering curriculum two basic courses on communications. Some universities do require a course in probability and random processes as a prerequisite. allowing both areas to be covered reasonably well in a one-semester course. This book is designed for adoption both as a one-semester course, in which the deterministic aspects of communications systems are emphasized with little consideration of the effects of noise and interference, and for a course that deals with both the deterministic and probabilistic aspects of communication systems. The book itself is self-contained, providing all the necessary background in probabilities and random processes. However, as stated earlier, if both deterministic and probabilistic aspects of communications are to be covered in one semester, it is highly desirable for students to have a good background in probabilities. Chapter 1 introduces a panoramic view of communication systems. All the important concepts of communication theory are explained qualitatively in a heuristic way. This attracts students to communications topics in general. With this momentum, they are motivated to study the tool of signal analysis in chapters 2 and 3, where they are encouraged to see a signal as a vector, and to think of the Fourier spectrum as a way of representing a signal in terms of its vector components. Chapters 4 and 5 discuss amplitude, linear, and angle, nonlinear modulations respectively. Many instructors feel that in this digital age, modulation should be de-emphasized. We hold that modulation is not so much a method of communication as a basic tool of signal processing. It will always be needed, not only in the area of communication, digital or analog, but also in many other areas of electrical engineering. Hence, neglecting modulation may prove to be rather short-sighted. Chapter 6, which serves as the fundamental link between analog and digital communications, describes the process of analog to digital conversion ADC. It provides details of sampling, pulse code modulation, including DPCM, delta modulation, speech coding, vocoder, image, video coding, and compression. Chapter 7 discusses the principles and techniques used in digital modulation. It introduces the concept of channel distortion and presents equalization as an effective means of distortion compensation. Chapters 8 and 9 provide the essential background on theories of probability and random processes. These comprise the second tool required for the study of communication systems. Every attempt is made to motivate students and to maintain their interest through these chapters by providing applications to communications problems wherever possible. Chapters 10 presents the analysis of digital communication systems in the presence of noise. It contains optimum signal detection in digital communication. Chapter 11 focuses on spread spectrum communications. Chapter 12 presents various practical techniques that can be used to combat practical channel distortions. This chapter captures both channel equalization and the broadly applied technology of OFDM. Chapter 13 provides a tutorial of information theory. Finally, the principles and key practical aspects of error control coding are given in Chapter 14. One of the goals for writing this book has been to make learning a pleasant or at least a less intimidating experience for students by presenting the subject in a clear, understandable, and logically organized manner. Every effort has been made to deliver insights rather than just understanding, as well as heuristic explanations of theoretical results wherever possible. Preface, International Edition, XIX. Many examples are provided for further clarification of abstract results. Even partial success in achieving this stated goal would make all our efforts worthwhile. A whole new world. There have been a number of major technology developments since the publication of the third edition in 1998. First of all, the cellular telephone has deeply penetrated the daily lives of urban and suburban households in most developed and even developing nations. In 1998, very few students carried beepers and cell phones into the classroom. Now, nearly every college student has a cell. Second, in 1998 most of the household internet connections were linked via low-speed 28.8 kilobits per second voiceband modems. Today, a majority of our students are connected to cyberspace through DSL or cable services. In addition, wireless LAN has made esoteric terms such as IEEE 802.11 into household names. Most students in the classroom have had experience exploring these technologies. Because of the vast technological advances, this new generation of students is extremely interested in learning about these new technologies and their implementation. The students are eager to understand how and where they may be able to make contributions in industry. Such strong motivation must be encouraged and taken advantage of. This new edition will enable instructors either to cover the topics themselves or to assign reading materials such that the students can acquire relevant information. The new edition achieves these goals by stressing the digital aspects of the text and by incorporating the most commonly known wireless and wireline digital technologies. Course adoption. With a combined teaching experience of over 55 years, we have taught communication classes under both quarter and semester systems in several major universities. In complementary fashion, students' personal experiences with communication systems have continuously been multiplying, from simple radio sets in the 1960s to the 21st century, with it easy access to wireless LAN, cellular devices, satellite radio, and home internet services. Hence, more and more students are interested in learning how familiar electronic gadgets work. With T.S. important need and our past experiences in mind, we revised the fourth international edition of this text to fit well within several different curriculum configurations. In all cases, basic coverage should teach the fundamentals of analog and digital communications, chapters 1 to 7. One semester course without strong probability background. In many existing curricula, undergraduate students are not exposed to simple probability tools until they begin to take communications. Often this occurs because the students were sent to Take an introductory statistical course that is disconnected from engineering science. This text is well suited to students of such a background. The first 7 chapters form a comprehensive coverage of modem digital and analog communications systems for average ECE undergraduate students. Such a course can be taught in one semester, 40 to 45 instructional hours. Under the premise that each student has built a solid background in Fourier analysis via a prerequisite class on signals and systems, most of the first 3 chapters can be treated as a review in 1 week. The rest of the semester can be fully devoted to teaching chapters 4 through 7 with partial coverage on the practical systems of chapters 11 and 12 to enhance students' interest. 1 semester course with a strong probability background. For curricula that have strengthened the background coverage of probability theory, a much more extensive coverage of digital communications can be achieved within 1 semester. A rigorous probability class can be taught within the context of Signal and System Analysis XX Preface, International Edition. C.F. George R. Cooper and Claire D. McGillam, Probabilistic Methods of Signal and System Analysis, Oxford University Press, 1999. For this scenario, in addition to chapters 1 through 7, Chapter 10 and part of Chapter 12 on equalization can also be taught in 1 semester, provided the students have a solid probability background that can limit the coverage of chapters 8 and 9 to a few hours. Students completing this course would be well prepared to enter the telecommunications industry or to enter graduate studies. 2-semester series without a separate probability course. The entire text can be thoroughly covered in 2 semesters for a curriculum that does not have any prior probability course. In other words, for a 2-course series, the goal is to teach both communications systems and fundamentals of probabilities. In an era of many competing courses in the ECE curriculum, it is hard to set aside 2-semester courses for communications alone. On the other hand, most universities do have a probability course that is separately taught by non-engineering professors. In this scenario, it would be desirable to fold probability theory into the 2 communication courses. Thus, for 2-semester courses, the coverage can be as follows. First semester, chapters 1 to 7, Signals and Communication Systems. Second semester, chapters 8 to 12, Modem Digital Communication Systems. 1/4 course with a strong probability background. In a quarter system, students must have a prior exposure to probability and statistics at a rigorous level. Cf. Cooper and McGillam, Probabilistic Methods of Signal and System Analysis. They must also have solid knowledge of Fourier analysis. Within a quarter, the class can impart the basics of analog and digital communication systems, chapters 3 to 7, and, in chapters 10 and 1-1, respectively, analysis of digital communication systems and spread spectrum communications. 1/4 course without a strong probability background. In the rare case that students come in without much background in probability, it is important for them to acquire basic knowledge of communication systems. It is wise not to attempt to analyze digital communication systems. Instead, basic coverage without prior knowledge of probability can be achieved by teaching the operations of analog and digital systems chapters 1 to 7, and providing a high-level discussion of spread spectrum wireless systems chapter 11. 2/4 series with basic probability background. Unlike a 1/4 course, a 2/4 series can be well designed to teach most of the important materials on communication systems and their analysis. The entire text can be extensively taught in 2 quarters for a curriculum that has some preliminary coverage of Fourier analysis and probabilities. Essentially viewing chapters 1 through 3 and chapter 8 as partly new and partly reviews, the coverage can be as follows. First quarter, chapters 1 to 9, Communication Systems and Analysis. Second quarter, chapters 10 to 14, Digital Communication Systems. MATLAB and Laboratory Experience. Since many universities no longer have hardware communication laboratories, MATLAB-based communication system exercises are included to enhance the learning experience. Students will be able to design systems and modify their parameters to evaluate the overall effects on the performance of communication systems through computer displays and the Preface International Edition XX. Measurement of bit error rates. Students will acquire first-hand knowledge on how to design and perform simulations of communication systems. Acknowledgements. First, the authors thank all the students they have had over the years. This edition would not have been possible without the much feedback from, and discussions with, our students. The authors thank all the reviewers for providing invaluable input to improve the text. Finally, the authors also thank Professor Norman Morrison, University of Cape Town, for suggesting a new problem PS 2.3 in this edition. B. P. Lathy. G. Ding Modern Digital and Analog Communication Systems. International 4th edition Introduction. Obeen Vergist Thay and simply past the decade, astounding. Scientific the community, rapid internet, expansion a Haas word permeated and of digital concept every communication once